talk for today. So we're having Sang-hyun Kim also from the Korea Institute for Advanced Study. We'll be talking about first-order rigidity of manifold diffeomorphism groups.
Yeah, thank you very much for the invitation. I'm always pleased to come to Cambridge, the home of Newton, Cavendish, Watson, Crick, Darwin, and Wittgenstein. And also I'm very pleased to be speaking in this wonderful tradition of MPCW. So I'd like to talk about first-order rigidity of manifold diffeomorphism groups. So it sounds like a logic, so maybe I'm also trying to corrupt you with the logics, but I'm more of a geometric topologist, and we really wanted to solve certain geometric topological problem, and we realized that mathematical logic could be of great help. So that's something that I'd like to share with you. So we consider groups from manifolds. There are many natural ways of defining groups. So, well, essentially, what is a group? If you just take anything in the universe and you just collect all their symmetries, it becomes a group. Right? So for a manifold, say, sometimes it is smooth, sometimes it's only topological for us. So we do not assume it is triangulable in general. And suppose you have a closed manifold, I don't really consider non-orientable ones in this talk. And sometimes I consider smooth volume forms or other structures, like topological or CK, or smooth or simplex, just whatever structure that you'd like to use. And you just consider all the structure-preserving homeomorphisms of M, and it's a group, right? Trivially. So especially I'd like to consider this kind of group as well, diff of R of M, where R is a real number, say R is K plus tau, where K is the integer and tau is a real number. So in this case, this should mean that the collection of CK diffeomorphisms such that the kth derivative is tau under continuous. So in terms of derivatives, for each real number you have a group, and also you can consider like R plus, which we really don't consider today. And other groups too, so all the structure preserving groups. And as a group theorist, we are very much interested in algebraic properties of these groups. More concretely, when are they isomorphic? So that is the base question. So if you have two different manifolds and two different structures, sometimes coinciding structures, when can they have the isomorphic or in certain equivalent structures? So I'm a bit overloading the term structure, but for me there are two meanings of structures. One structure is like omega, like CK structure, smooth structure, volume preserving structure. And another structure is more broad sense. In logic, structure means only one thing. It's just like the model itself, like groups or rings or field extensions. That is another use of structure. So here I'm talking about geometric structures. And when can two structures, geometric structures, have the same symmetry group as abstract groups? So that is something that I'd like to address. So there are two main motivations for me. Of course, there could be other motivations, but for me, the first one is reconstruction problem. So if we want to reconstruct the space or certain forgotten structure, here the structure really means mathematical logical structure, just model. So if you have a certain thing in the universe, X, and you just consider the set of its symmetries, structure preserving automorph bijections, then you have a function, structures, two groups. And reconstruction problem proposes to revert these arrows. So now you just remember groups only. So group is just big multiplication table. And can you reconstruct the forgotten structure from the algebraic information? So recover the forgotten structure from purely algebraic information. Of course, I should specify what I mean by information, and this is something related to our literal lesson that we learned. That from the beginning, actually, this is a logical question because we have to specify what we mean by information and forgotten. And mathematical logicians have been studying that kind of problem for a long time. So I wouldn't say much about math history because I'm not well aware of it. Just from my reading of Klein's Erlangen program, this is an essay, and there I picked the word symmetry and invariance. Essentially, well, I shouldn't really say much about history, especially when Carl Friedrich is present. The essence of the geometry is the symmetry. You have to understand at that time, projective geometry, you have to consider the group and understand it. Slightly more concretely, there are many rigidity theorems which can be formulated in terms of reconstruction problem. Malchev for nilpotent groups, Selberg, Bayou, Calabi for lattices, Gaulian Raghunathan, all these great rigidity theorems can be formulated in terms of certain form of rigidity or reconstruction. So lattices as a group, purely algebraic object. So can they reconstruct its ambient Lie group, G, very broadly speaking. So many of the relevant researchers are present in the audience as well. And also Borel conjecture or Hilbert fifth problem. I'll slightly talk about Hilbert fifth problem later. So essentially Hilbert fifth problem, what is it? It just proposes that locally Euclidean topological group is a Lie group. So you consider C0 structure and group structure, and when they are compatible, there's a hidden C infinity structure which you can reconstruct from the given information. So they can be also formulated as a Hilbert reconstruction problem. And the second motivation for me came from consideration of big countable groups. So of course these are very vague terms, but in the case of lattices, people often consider lattices as big groups in higher rank or high rank Lie groups. So Zimmer proposed the conjecture and Berger Monod in 99 and Gis about the same time for dimension 1, and Brown Fisher Taylor considered the higher dimensional manifolds, and the conclusion is the rank B plus on lattice under mild conditions cannot act by C1 diffeomorphisms on D-dimensional manifolds. So these are considered, these red words are supposed to mean big groups. And also there is an outstanding conjecture. People attribute this to Gromov, that random groups cannot act on manifolds, but surprisingly little is known about this conjecture. So I guess it's known for real line, but not much more than that. So of course cannot faithfully act on manifolds. So it is conjecture. And also so mapping class groups are often considered as big groups. So we consider them, and these so-called non-stupid mapping class groups, so non-virtual free mapping class groups, can never virtually act on the circle by C1 plus tau diffeomorphisms, where tau is a real number. And even after taking a deep finite index subgroup, there's all these algebraic obstructions. It doesn't admit any faithful group homomorphism, injective group homomorphism into the diffeomorphism. So I should note that this diff R is a group for R at least 1. But if you consider R less than 1, this simple exercise is not a group. It's not closed under composition. But if R is at least 1, you can use chain rule and prove that it is a group. They form a group. If you compose two CR diffeomorphisms, composition also CR diffeomorphism. So on the right, you have group, or just, oops, what did I press? On the right, there's a direct limit of groups. So you can talk about group homomorphism. And even if you go into very deep finite index cover, you can never find the embedding. So in 2016, we proved it for C2, and later we realized that C1 plus tau is not even possible. And outstanding conjecture is C1 is not even possible. So that's related to Ivanov conjecture. So if Ivanov conjecture is true, then you can prove that it does not admit C1 embedding either. And also another, from this we started to consider countable subgroups of manifold diffeomorphism groups. So we also consider that it's reasonable to expect that moderately big groups can only act geometrically. Of course, what does that mean? So we only to consider lattice-like subgroups of manifold homeomorphism groups. So one showcase of that would be SL2Q or SLMQ. So let me consider just SL2Q first. Yeah, some of this home of Newton and Cavendish didn't invent the right joke yet. So SL2Q, consider homeomorphism. So, and according to that line, moderately big groups, and considering SL2K as moderately big groups, this rho should really go through SL2R. And this is natural values. So that this would be one instance of that claim after semi-conjugate and after semi-conjugacy. And that is actually true. So we try to prove this, and we proved it and recently and discovered that actually it was known 20 years ago by Bader Furman. Their unpublished paper around 06. This is one instance of big groups, big countable, not necessarily finite general groups, but you have a big countable groups of manifold homeomorphism or diffeomorphism groups, which remembers its ambient manifold homeomorphism groups. And for the one manifold case, either circle or compact interval, so we also consider CR structure, and we discovered that finitely, even finite, you can encode the CR structure to a finite generated subgroup. So for each real number R at least 1, you can find finitely generated group, gamma R, inside C1, CR diffeomorphism manifold to one-dimensional manifold, such that it remembers the real number R. So you can never embed into any higher regularity one-dimensional diffeomorphism groups. So these are all the motivation that I had. So we wanted to find certain big countable subgroups of manifold homeomorphism groups or diffeomorphism groups which kind of remember its ambient manifolds and even regularity or structure. So in the manifold case, actually many things were known. So we take this 1963 annals paper that for compact manifolds, isomorphic homeomorphism groups imply homeomorphicity of the manifolds. But here, it's really compact topological manifolds. You do not assume anything other than that. So, like no smooth structure or no PL structure. So, but you need compactness, because if you forget compactness, there are many silly, sometimes even non-silly examples. Silly example would be homeo of the real line is isomorphic to homeo of the compact interval. So you need compactness, and also people wanted to extend this to non-compact case, which restrictions or which varieties they can have. And also in the case of diffeomorphism groups, Takens, so they didn't write paper together. Takens wrote C infinity case, this is dynamist, and Philip Kavitz wrote this PQ case, integer case. So if you have a integer which is either at least 1 or you allow infinity, and if you have a compact closed manifolds, then the diffeomorphism, it's the abstract group theoretic information of CP diffeomorphism group remembers the number P and the manifold N up to even diffeomorphism, CP diffeomorphisms. And recall that two manifolds are CP diffeomorphic, and they are actually C infinity diffeomorphic, because every C1 structure even supports unique C infinity structure of the conjugation. So yeah, in the end, you can just say M and N are C infinity diffeomorphic, but also the point is that this isomorphism should be necessarily induced by certain this mysterious diffeomorphism between the manifolds. So that is the content of Takens-Philip-Kavitz theory. And actually, if you look at the, so this theorem can be proved in a in a very short way, even like 1 or 2 pages after using certain theorems that I will introduce later. So the natural question is, what about the real number? Actually, that is the motivation that we started with. So we wanted to extend this to the real number.
Just out of curiosity, so if you have this P of n, can you sort of abstractly theoretically characterize stabilizers of points as being maximal subgroups?
Yes, very good point. So that is how the proof started. Yeah, actually, that's a very good point. So actually, there are two, even Whittaker's theorem and Takens-Filipkevich theorem. Yeah. So Whittaker used similar idea, and they used the similar. Filipkevich used a similar idea of they started the point stabilizer and mapped the point stabilizer to the right-hand side and prove that it is point stabilizer as well. But later, there is a much simpler proof that I'll talk about later. So our motivation is what about the real number case? And the Takens or Filipkevich proof doesn't apply because they strongly use the fact that P and Q are integers because they are using actually some variation of Hilbert problem known only for integer regularity. So we cannot extend their results. And so that is how our work was motivated mainly. And by the way, so in the manifold case, Banyaga even wrote a whole book now about this manifold reconstruction for all the structures that you can think of. Volume preserving, smooth volume preserving, or measure Oxtoby-Ulam von Neumann volume measure preserving, or contact homomorphism, or simplex homomorphism, or all kinds of variations. And he proved all that using deep results of these people and wrote a whole book that is the problem that I mentioned, this manifold reconstruction is solvable for all these structures. So, and then Rubin was a logician in working in mostly 1980s and 1990s, and he proved this beautiful theorem which greatly generalizes Whittaker's theorem. So we say a group is, he said, a group is locally dense if it is dense somewhere. So I should introduce a notation, one notation there. And so this, some people call this as rigid stabilizer. So if G is a homeomorphism group of certain space, then Gx simply means the collection of elements supported in U. So support is, of course, complement of the fixed point set. And locally dense means whatever small open set you consider and whatever point you consider, so GU has some, is not nowhere dense there, is somewhere dense there. So that's the meaning of locally dense. Whatever point and you consider is local stabilizer, orbit of the point is somewhere dense. That's all. So it's a relatively mild condition because it's easily satisfied by diffeomorphism groups or volume preserving diffeomorphism groups, or even volume preserving diffeomorphism groups isotopic to the identity as well. So it's a very mild condition. Of course, homeomorphism groups as well. Any groups containing these groups satisfy locally dense, or like you consider PL homeomorphism groups as well. Or Thomson's group T acting on the circle, it is also locally dense because whatever open set you consider, you can densely fill certain open set. And Rubin's theorem is that under the hypothesis that G acts locally densely on locally compact Hausdorff and perfect. Perfect means just no isolate point because using isolate point you can make silly counterexamples. So locally compact Hausdorff and perfect space, or even some bare space, then the action is unique and the spaces are homeomorphic. So G indeed remembers X and Y. Then you have a G equivalent homeomorphism, H, X to Y. So another way of formulating this theorem is if you have two isomorphic groups, G and H, acting on X and Y, then the group isomorphism between G and H must induce certain homeomorphism or must be induced by some mysterious homeomorphism between them. So this is the almost as good as it gets. The group reconstructs the space. The group remembers where it came from, as long as the actions are assumed to be locally dense. So this easily gives the proof of Whittaker's theorem, right? Because homeomorphism groups are acting locally densely. So if you have two homeomorphism groups isomorphic, then it's trivial consequence that the spaces are homeomorphic and isomorphism is induced by that G-covariant homeomorphism. And so here's the story for me. So with my collaborator Thomas Cobretta and I wrote a certain introductory book about manifold reconstruction, mostly for one manifold. And at the time, I was maybe he was more familiar, but I wasn't really familiar with the logic. But Rubin's theorem is proved it using the terminology of mathematical logics. And I was so unfamiliar, so I just deciphered all the logics there, and then reverse engineered all the proofs so that in the end that there are no logics left, and we wrote completely topological proof in the book. But and later we realized that actually Rubin's proof is the right proof. Instead of just deciphering and reverse engineering everything, just using the logics terminology and their viewpoint and framework is the right way of compressing things. Otherwise, you can easily get lost. Sometimes it's like it's easier to build a paperclip factory rather than just making a paperclip by yourself. So that is the lesson that I learned. So let me tell you a bit about the first order logic. So many of you are just more familiar about this terminology. So in mathematical logic or first order logic, language is just concatenation of symbols. So in short, logic is just combinatorics of symbols and combinatorics of sequences of symbols. There are logical symbols like for all, exists, or and or implies. And there are non-logical symbols, but some part of non-logical symbols are also common, like variables. So traditionally people use x0, x1, x2, and so forth. But let us use G for the group elements. And now signatures are structure specific. Constant symbols, function symbol, relation symbol, and arithmetic function. So in the group case, signature means constant symbols. The symbol 1 will be used to mean the real, actual identity element of the group. Function symbol, there are two function symbols, compositions and inverses, and relation symbols, equality. So equality is somehow redundant as well. And now you have a combinatorics of sequences of symbols. That is first order logic. All right, arithmetic function remembers the arities of the function symbols. So composition is two variables and inverse requires one variable. And formula, so we need to define what the formula is. So I'll not define what the formula is rigorously, but formula is some recursively defined certain sequence of symbols which are meaningful. Some finite sequence of symbols which make sense. Right? So for example, for all B, AB equals B. And of course this is false most of the time, but formula anyway. So it is valid or not valid. And even A is not quantified, which is fine, so that's formula. And sentence is a formula which has no unquantified variable. So for all A, there is B, AB equals BA. I'm not talking about whether this is correct or not, I'm just talking about what the formula is. And by design, each sentence is either true or false for each group. So that is how they are designed and recursively defined. So formula sentence is either true or false. And non-example, for all A, there is some integer n, for all integer n, there is some B such that B equals A to the n. So this is, of course, true statement in all groups. But it is not a group theoretic, in the group theoretic language, because we are not allowed to use this membership symbol or positive integers set symbol. So these are, or infinite conjunction of sentences are not also allowed. We are only allowed to use finite sequences of these symbols. And then we just collect all the valid sentences in a group. So that is called theory of group. And so this is countable set, but huge set. Right? So for example, in an abelian group, if group is abelian, you can say theory of Z2 contains for all G1, G2, G1 commutes G2, but also G1, G3. I mean, in case you're not familiar with methodologics, you consider all these stupid redundancies. You just maximally collect them all. But still, it contains all the valid sentences of a group. And two groups are elementarily equivalent if the theories coincide. That means any theorem with just in terms of these symbols hold in one group, also in the other. Or first order equivalent. So we will use triple bar to mean elementary equivalence. And like this is not so much related to my talk, but just for an introduction, there is the famous Tarski problem asking whether non-abelian free groups have the same elementary theories, elementary equivalent or not. So it's stood for almost 60 years, 60 plus years. And then also the question, his second question was that it is really decidable. So in other words, yes, and it is positively solved by Sela and Kalapin-Myasnikov after 66 decades. And also there are many other non-free, but elementarily free groups, like hyperbolic surface groups. And this decidability, I mean, that is oracle function. So given a sentence, true or not, you just decide whether it is true or false in the group G. So it is you take a sentence and output truth value of in the G, phi is true. That's what this symbol means. In the G, phi is true or not. And it is very important to question whether this is also Turing machine or not, or Turing computable or not. And now, so in the free group case, there's certain flexibility. So we saw certain flexibility and rigidity results in our previous talks. So here too, so free groups are flexible. They can be elementary equivalent. And on the other opposite extreme, there's a rigidity. So group is first order rigid in a certain class of groups. If any other group can only elementary equivalent to that, only if they are isomorphic. So unless they are isomorphic, it can never be elementary equivalent. So that's the first order rigidity phenomenon. And there's a very fruitful direction of research considering first order rigidity finite generic groups. For example, Avni, Lubutsky, Mary proved that non-uniform higher rank, and I guess some uniform case as well, arithmetic lattices are first order rigid in the class of all finite generic groups. And Thompson's group of F or T or even linear groups in a somewhat loose sense up to elementary equivalence of the field, or finite generic commutative rings, so not necessarily groups. You can also consider ring structure as well, and also even certain algebraic curves as well. They are first order rigid. So what we are considering is really this. So you have a manifold and structure. You forget most of the structure and only remember the group. And you forget the group and remember only their logical structures. And the logical reconstruction problem proposes to revert this error. So given a manifold with this structure, you only remember the true sentences in the group. And can you reconstruct the manifold and structure? And so can you recover this forgotten information? So broad questions is actually I don't know, I have no idea how to prove it, so I'll just ask it as a broad question. So if you have just two structure, m and omega and n and theta, an elementary equivalent, so these elementary equivalents can imply the omega equals theta and omega equivalence of m and n under certain class. So that is a very broad, irresponsible question that I can make. Or you can have a research problem generator. So we've been sitting through many rigidity results even in this conference, right? You have a certain equivalence and can you reconstruct the original structure? So you just take a classical theorem on the isomorphism of homeomorphisms. Like even you just take the Banyagas book that I mentioned. They are full of such theorems. And take your favorite structure, simplector or volume preserving, or CK or CR, and then prove your theorem on the elementary equivalence. Can you weaken the hypothesis by replacing isomorphism by elementary equivalence? And can you prove still the same reconstruction theorem? This might sound like a daydreaming, but I'd like to introduce some incidents of this phenomenon.
But wouldn't it be, instead of having rigidity, having flexibility, like that you know that for a whole class of manifold, it suffices to prove something on the homeomorphisms of the circle, and then you have it for all the other manifolds. I mean, that's typically what happens.
Yeah. So I mean,
Real closed fields.
Yeah. But I'll just mention a bit about the high-dimensional manifolds as well. And there are certain rigidity that I'd like to introduce. So first part, there are two parts of our results. And combining these two parts, we will make a certain rigidity results. The first part is manifold recognition. So suppose you have a closed, connected, smooth manifold M. Then we prove that there exists a group theoretic sentence, DM, such that whenever you have a group G between this reasonably small group, C infinity isotopic to the identity, and C1 diffeo, so in between anything, then they all satisfy this sentence. And on the other hand, if you have a certain mystery manifold and mystery group satisfying this inclusion in between, and if that group satisfies, this VM is also satisfied in that group, then M and N are diffeomorphic. So they are smoothly diffeomorphic. So that is the part A of our results. So this is the solution for the differential structure. And of course, I cannot really write it down. So that's why I'd like to talk about this, my teacher lesson that I got. So using logics, you just compress and bootstrap and bootstrap and bootstrap things. Because this sentence is like, I am diffeomorphic to M, or my ambient manifold, I came from a manifold M. And it's not easy to write that down in terms of pure group theoretic symbols directly, but you'll have to bootstrap or recursively define the sentences. And also, we also have a C0 version of topological manifolds, even without assuming that the manifold is triangular or smooth. So trivial corollary is Whittaker's theorem, so we didn't use Whittaker's theorem. That manifold isomorphism implies homeomorphicity. And also another corollary is the Chigurh-Kister, this same Chigurh that we saw in one of the first few talks. So Chigurh-Kister proved that there are only countably many compact topological, possibly non-triangulable manifolds of homeomorphisms. So of course, triangulable is easy. It's obviously countable, but even non-triangulable, so there are only countably, up to homeomorphism, there are only countably many compact topological manifolds. So they proved it in 1970 with using a very deep theorem of Edward Kirby on isotopic extension theorem. So their paper is relatively short, 6 pages or so, but they use very deep C0 topology of 1970s. So this is corollary. I'll just first say that this is corollary because whenever we have a manifold M, we produce a sentence. And by definition, there are only countably many sentences in the world because they are all finite sequences of symbols. Therefore, trivially, there are only countably many compact topological manifolds by this remark and countably many smooth structures in the world. So that is the obvious corollary. But I cannot say that Chigurh-Kister theorem is our corollary because we use the key component of their proof. Actually, we looked at their paper and their paper reduces to certain lemma, and we use the variation of that lemma. We are not recovering their theorem, rather we are using it. And part B is regularity detection. So if you have a close connected smooth manifold M, right, I'm just repeating what I wrote. So part B is if you have a closed smooth manifold M, and whenever you have a rational number Q, or actually more, you can relax this number. You can say Q is computable or definable, but anyway, rational is fine for us, for our purpose. So for any manifold and rational number pair, you can produce a sentence, finite sequence of group theoretic symbols, such that whenever regularity is not as good, so the group is big enough, right? So if regularity decreases, the group gets bigger. So whenever the group is big enough, then PMQ holds. PMQ is in the theory. And whenever the group is small enough, that means the regularity is larger than Q, so it is a better regularity than Q, CQ, then PMQ does not hold. So this sentence is essentially saying that I have a just CQ diffeomorphism in some sense. So I'm CQ, but no better than CQ. So that is what this PMQ is supposed to say in terms of group theoretic sentences.
But your theorem says there exists a sentence?
Yeah, I mean,
or I produce a sentence.
Right, so that is a very good point. So in general, we cannot, because we use Chigurh-Kister theorem, and Chigurh-Kister theorem uses Edward-Kirby isotope extension theorem, and Edward-Kirby isotope extension theorem, there's certain existential part. Maybe it can be more concretized, but as far as to my understanding, it is existential theorem in Edward-Kirby isotope extension theorem. So also we cannot. There is such a thing. So Chigurh-Kister gives a certain epsilon, but we don't know what epsilon is, or we cannot compute algorithmically.
Even concrete examples of manifolds.
A concrete example for circle, we can do that. But torus, I think it's a good question. But higher that, I have no idea. So combining these two, so we have the main theorem. Main theorem is that they are really first order rigid. So if you have two smooth manifolds, plus, and we have only to assume that one is closed and connected, then it will follow that the other is also, so is the other. And R and S are real number, or 0, or infinity. So number between 0 and 1 are excluded because of this non-group property. Then elementary equivalence arises only when everything is the same. So R and S are the same, and I really should say M is C infinity diffeo to N, because even C1 diffeo implies C infinity diffeo. Because this C1 structure, maybe this is the first remark. It's the classical theorem that every C1 manifold supports on unique smooth structure. And another remark is that, as I said at the beginning, so our main motivation was even with a stronger hypothesis that they are isomorphic, we weren't able to resolve for the real number case. It was only known for integer case. And recovers Whittaker's C0 rigidity theorem and Takens-Philip-Kavitz as well for integer case. And also, I'll not talk too much about it, but you can prove the same for CR diffeomorphism group, which are preserving smooth volume forms. And also C0 homeomorphism group, preserving good measures. Good measure means this nowhere zero, boundary zero measure, Oxtov-Ulam measure, so-called. Right, so let me give a brief proof of these two theorems in 10 minutes. So let me give you a fake proof. So this is the theorem A. So what do you want to say? Well, we just said that VM is, this manifold is diffeomorphic term, right? Under this hypothesis, closed connected smooth manifold. Just pick an English sentence that this manifold is diffeomorphic term. But this is not a proof because like this manifold is diffeomorphic. They are not group symbols. We are only allowed to use group symbols. So we have to devise a certain method to produce group theoretic interpretation of this English sentence. So this is somewhat reminiscent of Gödel sentence, right? Gödel sentence, what is it? It's purely arithmetic sentence in terms of just pluses and minuses and logical symbols saying that I'm not provable. This sentence is not provable. But we don't succeed in finding such a sentence. And like there are computer programs now producing such sentences. So we are doing something like this. So we would never be able to actually write down the sentences concretely, but we just prove the existence. Ingredients are, as I said, picture lesson is purely logical observation that Rubin made before. So if you have a locally dense, so under this certain mild hypothesis of group action, support E is slight variation that Rubin used for his own advantage. So support E simply means, support EG simply means interior of closure of the support. And by taking closure and interior, we avoid this kind of silly example. So in this case, if you take closure interior, it changes, right? If you are missing, say, the boundary, by taking closure and interior, this boundary point will disappear. So he wanted, then actually the whole point is that, so if he wanted to only consider open sets of this form, where interior of the closure coincide with. These are called regular open. The nice thing about regular open is they form a Boolean algebra. So you can take minuses and pluses and joins. And he was an expert in Boolean algebra automorphisms and logical properties of it, and he uses the logical properties of Boolean algebra. Actually, he proved his theorem. And the key step is this. So if you have a locally dense section, then inclusion of supports is actually group theoretically expressible. So there is a certain group theoretic sentence which is equivalent to saying that their supports are, one is contained into the other. But for the proof of Rubin's expressibility theorem, just no logics are used. It's purely topological, really point-set topological theorem. So I cannot say it's exercises because it's quite involved. It's several pages if you write down the whole proof. So let me just summarize what the sentence is. So we just define this very complete. You don't have to read it. Just complicated first order sentence. That's the whole point. And so if F is given, we define certain set eta G of F as the collection of group elements satisfying whenever H is not in the center, you can find two elements such that it satisfies certain first order sentence. So you don't have to read it, as I said. It's in my book. You can purchase my book. You don't have to read it. And then support is, one of the support is contained into the other if and only if H is contained the centralizer of the 12th power of elements in that set. So it's very complicated first order definition, but there exists first order sentence. That's the whole point. And Rubin's point is just logics. So you wanted to find certain first order expression that one support is contained in each other. It's really magical. I really don't know a short proof of this. My proof at least requires 3 pages and more actually. But so it's hard point-set topology exercise. Hence, for example, this restricted stabilizer. So G of open set can be defined in terms of purely group theoretic definition. So it's definable, so-called, in logics. And well, I wrote key step, but key step really doesn't make much sense anyway. But if G is in F, then support of F and G cubed and G fourth are disjoint. So this is kind of like, if you write the whole 3-page proof, it's right in the middle. That's all. Anyway, so then he considered action structure. So we have group structure. Now he expand the collection of symbols. Here he was using more variety of symbols. So universe, there are 2 elements, either group elements or all the regular open sets. And signature, he was able to do the Boolean constructions, Boolean operations. So O plus simply means almost like union, but you regularize it so that it becomes regular open set in the end. And also there's a symbol for extended support. between G and U. So this is binary relation. And also group action, triple ternary relation. W is G image of U, and also inclusion. So you have more symbols you are allowed to use in this new structure. And Rubin's expressibility theorem simply means that action structure is interpretable in G, which means that although you seem to have more expressibility with these new symbols, actually mathematics got no stronger. So that's the meaning of interpretability. So the oracle of this new structure is no stronger. So they are no smarter than the group theorist. So that's the whole point. The oracle didn't get stronger. So math is the same, but it's just you seem to have more expressibility power. So that's, and then it's much easier to write down the proof. For example, here's an exercise. So M is connected. It is expressible. Right? So now we consider, I think, I don't have much time, like 4 minutes, but I think this is, am I supposed to jump? Because this is just good illustration of what's really going on. So I'll just give this proof that connectivity of the manifold is expressible. And then we express compactness, we express boundarylessness, and then we just trying to encode all the topology, even without the assumption of the triangulability in groups. So let me say M is connected. So again, the running hypothesis is that, say, G is mildly big and mildly small. So here 0 means isotopic to the identity. Then M is connected if and only if so I'll be considering two open sets, U and V, and I want to claim that they are not disconnection. So how do I do that? So for all disjoint open, actually regular open, U and V, there exists U prime, of course non-empty, U2 prime disjoint in U, of course non-empty, and some group element such that GU prime goes into V, but GU2 prime stays. So see, here's U, here's U prime, here's U2 prime. And G is mapping U prime to GV, but staying. And you can easily convince yourself that this is equivalent to saying that the manifold is connected. You can move to anywhere, and you can also consider a volume-preserving version of it, although it is slightly more involved. You can do that. Compactness is, do I have time? Compactness is also easy. I mean, yeah, so I don't really have time, but yeah, compactness is also expressible by group theory, and then we do many properties of the manifold in groups. So this process is called expansion in general. So they call it conservative expansion, meaning that oracle is not get stronger, but you seem to have more expressibility power as the conservative expansion. So more powerful language we got is action structure, but actually for our purpose we need a lot more powerful expression. So we need the real number. You should be able to express all the continuous functions, manifold, any countable points inside M, and this exponent function. So they are not a priori expressible in group, but we conservatively expand it so that you can use these symbols without making the oracle get stronger. So the part 2 is meaning that oracle is no might here. Then we interpret Phi star to group theoretic sentence. So Phi star is a new sentence saying that it's powerful enough that you can express I'm diffeomorph to M in the end, because I'm allowed to use so many symbols, but still we can express it. So in terms of this, Wittgenstein taught at Cambridge for like 10 plus years, and in his treatise, logical treatise, he said mathematics are all tautologies. So he didn't really care much about mathematics. But later he changed his mind. It's still tautologies, but
Admiration for the fact that they are tautologies. He was very,
well, if you read
very
the
suspicious of philosophy.
right. So I mean, there are two parts. His mind changed. I mean, later he said that like still tautology, but very meaningful discovery of the rules in the world. But when he was young, he just said it's just tautology. Like whether Liar's paradox is true or false, he doesn't care because it doesn't say anything about the world. Anyway, so I'll just say about Chigurh-Kister variation. So because this is also key step. So Chigurh-Kister theorem for C-infinity version is that here's this. So suppose you have two manifolds, say genus 2 surface in R3. And Chigurh-Kister theorem says that you cover it with balls, disks, like topological disks. And they are saying that there is an epsilon such that if you perturb each disk by epsilon, then probably it's not a manifold. And if the result happens to be a manifold and the epsilon is small, then the genus should be still 2. So that's their theorem. So whenever you have a ball cover of a manifold, there is an epsilon such that if you perturb balls very little, then the result should be homeomorphic, or in our case, even diffeomorphic with slight variation, as long as the result is also a manifold. So this is how you prove manifold recognition. And I'll just skip, and there's the regularity recognition is using just Harrison's diffeomorphism. She proved that for any higher dimensional manifold, you can always find just CR diffeomorphism. So this is her annals paper in 75 and generalized to 79 to any manifold of higher dimensions. So I'll stop here. Thank you very much.
Questions?
So your rigidity thing for compact manifolds, you need at least C1 diffeomorphisms, right?
Good point. So we proved actually two separate theorems. So one is purely C0. We don't even assume triangulability.
Okay, so there is a homeo.
Right, homeo theorem and also C1 or higher theorem.
Okay.
Right, so
But just not intermediate.
Right. And for closed, for compact, I think it is very interesting question, but we couldn't solve it, compact case, because we don't really have a good way of expressing things happening on the boundary or smooth structure involving the boundary. So compact case is very interesting, but we couldn't solve it. And also you might want to ask the non-orientable case because we always assume used volume forms. For non-orientable case, I just say I have no idea because this is I think it's yeah. Non-orientable case is just out of my imagination.
Is there some relation between profinite rigidity and first order rigidity?
What was the question?
Alex is the right person to answer.
Is there some relation between profinite rigidity and first order rigidity?
The only answer I can give you that the theorem that was quoted there that we showed that finitely that the non-uniform high-rank lattices are first order rigid is actually results of our failure to prove that for finite rigid. What nice in mathematics, when you fail, you can present it still as a success. Write a paper, because we started really, we wanted to prove for finite rigidity for them, and we were not able, but somehow in the middle we realized that we can prove first order rigidity, it was kind of surprised because at that time nobody expected such a strong result.
Okay, so it shows
It
like
turns
maybe,
out that it is, but but it's not true that it's weaker than finite rigidity. I mean, they are somewhat related, especially in the case that you have bounded generation. You see, just compare it to the results of Sela. Free groups are element equivalent, but they are not for finite rigid. They are not for finite equivalent, of course. So I don't think there is some.
So I can say a few things like.
What? Well, they are not, but they are kind of within, like within the immediate. All the examples are within the lattices. Like
Yeah,
Aka,
lattices.
right, yeah.
Alex also proved that topologically finitely generated profinite groups are elementary rigid.
So is it
So you proved that topologically finitely generated profinite groups are elementary equivalent.
Yeah, for
Profinite
profinite
groups,
they are elementary.
Yeah. So there are certain cases for profinite
Thank
groups.
you for reminding me.
Yeah. Also, like this week, I also from Alex, I realized that this finite subquotient set. So given a group, you consider all the set of all the finite subquotients. Then it's elementary equivalence invariant. So some subgroup surjects onto this finite group. So that is expressible in first order sentence. So for example, you consider certain groups that do not contain free group, and it's meaningful invariant.
Are there more questions? Yeah, just a very, very quick one. Who's that?
Oh, I don't know. ChatGPT claims it's Newton.
It looks like the guy in the portrait.
It's kind of explained by the numbers. Lots of cases.
Are there more questions or comments?
I have another question. So if you take this elementary theory of a group, is there some method on this kind of formulas and sentences?
Well, I mean, one loosely related question that I got is the VM that I generate, can it be used as a topological complexity? The length of the shortest length of the sentence saying that I am homeomorph to M. Is it a topological complexity? I have no idea. I think it's a very good question. And just, naive guess is this sentence should get longer and longer as manifolds get more complicated. But our proof, again, uses certain existential results. So I don't know how to measure them effectively.
More questions?
Somebody told me that for certain examples, you can make it concrete. Could you elaborate on that? Which ones?
No, it is still long. Okay. I can show you maybe compactness recognition. That could take 3 minutes, but circle is already complicated.
Do you have any information about the sentence?
Any information about
The sentence. For instance, is it a sentence that has how long it is?
right. So as I said,
is it a positive sentence?
So as I said, for circle, you really don't need Chigall-Kistler, but higher dimensional manifolds, we use Chigall-Kistler theorem, which is existential. There's some mysterious number epsilon. Not that it's mysterious, but it is mysterious in the sense that it is using certain Edward-Corby extension theorem, which uses existential result. So we cannot concretize it.
How about the number of alternation of quantifiers?
Right. I think that's a good point. I think we can do that. I mean, probably for even torus, it could be more than 1,000 if we follow our argument. But still, it could
Maybe
be
it doesn't grow.
Yeah,
with
it could be
the
measurable.
natural.
Yeah,
Maybe just with the damage.
right. Yeah, this. Actually, no. I think yeah, this plausible. This plausible. We certainly use a certain number of balls to cover a manifold, but it's plausible that alternating occurrences are the same. It's plausible.
Okay, let's maybe continue the discussion outside. So let's thank Sam again.